So far, we've been talking about the limit in a very loose kind of way. In this lesson, we're going to look at a more formal definition of the limit. So let's start just by thinking about an example. Let's imagine we have the function x squared. Now, we know that the limit, as we approach 2, equals 4. Now, what if I ask, how close does x have to be to 2 in order for f of x to be within 1 of 4? That means, for what range of x do I get an f of x in the range 3 to 5? Now, the way I can find that is I can just plug in numbers and solve for x. So f of x equals 3 gives me x equals 1.732. I just found that by taking the square root of 3. And similarly, f of x equals 5 means that x equals 2.236. Now, the distance of this number to 2 is equal to about 0.268, and the distance of this number to 2 is equal to about 0.236. So what I can say is that as long as x is within 0.268 of 2, then f of x is within 1 of 4. Now, we have a special name for these values that specify how close we are to x and f of x. We call the distance from x delta, and the distance from y we call epsilon. So in our first case, where we specified that epsilon had to equal 1, that gave us that delta would equal 0.268. Now, what if I want to choose a different epsilon? I don't think within 1 is very close to 4, and I want to be closer. So I'll choose an epsilon of 0.1. Now, how do I find my delta? I'll just do the same thing. I can plug in my range for y. So now my range for y is 3.9 to 4.1. And so if I plug those values into the function, what I find is that x goes from 1.9748 to 2.0248. And so our first number is a distance of about 0.0251 from 2. And our second number is a distance of 0.0248 from 2. So since this number, our distance, is bigger, we're going to use that as our delta. So we find that if epsilon equals 0.1, then our delta must be 0.0251 in order for our y to be in the range that we want it to be. Are we beginning to see a pattern here? What we're seeing is that for any epsilon that we're given, then we find the delta by saying our y range is 4 minus epsilon to 4 plus epsilon, meaning our x range is from the square root of 4 minus epsilon to the square root of 4 plus epsilon, and our distance from 2 is equal to 2 minus the square root of 4 minus epsilon, take the absolute value, and our distance from 2 here is that, and we found that this value is always going to be larger, so we'll use that as our delta, meaning that our delta always equals the absolute value of 2 minus the square root of 4 minus epsilon. So what this tells us is that no matter what epsilon I choose, I can always find a delta to satisfy it. This is what it means that the limit as x approaches 2 of our function x squared equals 4, that for any epsilon we can always find a delta. Now we're ready for our fancy definition of the limit. When we say that the limit as x approaches a of a function equals L, what we're essentially meaning is that for any epsilon, I can always find a delta such that for any x within delta of a, f of x will be within epsilon of L. Now we're going to get even more fancy and replace this statement with the mathematical expression x minus a is less than delta, and similarly we're going to take this expression and replace it with the mathematical way of saying it, which is that f of x minus L is less than epsilon. Now we just have to add two technicalities. Epsilon and delta both must be positive. So what that means is that we'll add a 0 here. And now I'm just going to add one minor technicality, that epsilon and delta both must be positive. So now we have, for any epsilon greater than 0, there exists a delta greater than 0 such that the absolute value of f of x minus L is less than epsilon when the absolute value of x minus a is between 0 and delta.